Okay, this is a much misunderstood topic that I go through every semester to help clarify this idea. And once we go through these slides, I hope that some of the concepts will stick in your mind. I like to start with an example. I'm designing a search engine. I want to overtake Google as the top search engine. I think I'm smarter than everyone at Google, and I think my idea is going to really, really work. That's not true, by the way, but let's say it is. Let's say I really think I can design a better search engine. Do I want my runtime to look like this yellow line here? Do I want the runtime to look like red? Do I want it to look like the blue? What do I want my runtime to look like? And this is where big O comes into play. But essentially, it's the runtime of your algorithm. So on the left-hand side, I think of this as time. So I look at this time here. So this might be seconds, milliseconds, something like that. For simplicity, we'll just say it's seconds. And then over here on the X, we have the number of items. Right here, we have one object. Right here, we have 500 objects. When I'm trying to rival Google and create a search engine that searches for things really fast, what big O notation would I like my search engine to be? Well, let's take a look, because a lot of people initially say, hey, I think I want this, just because it's one of the extremes. Not many people actually say this at first, and no one really says this. They either pick this one or this one. Let me tell you why this one is not what we want our search engine to be. When I have, let's say, 75 items that I'm searching through, if I follow 75 up to here, it's going to take 600 seconds, which seems like a lot. That's not going to help me overtake Google as the top search engine. What's interesting about this is, let's say I have 200 objects, and I go up and I go up and I go up. I may never hit, it may hit this, but this is exponential growth, and I'm not going to hit this. It's just going to time out. Nothing's going to work. If I was doing this down here, this 0, 1, this is called constant time. So no matter how many objects I have, I could have 1,000 objects. It's going to take me the same amount of time to search through 1,000 objects that it would if I was searching through one object. Now let's look at this N. So this is what we call linear growth. Let's go back to the 200 objects. If I have 200 objects and I go up to the Y, it's going to take 200 seconds. If I have 400 objects, I'm going to have 400 seconds. So you see it's a 1-to-1 ratio, and that's why it's linear. Now, what did I put this yellow box in here for? What is the purpose of this? Some of our programs that we're writing, especially as beginners, this is not going to come into play. We're never going to see this. Because we have such a few number of objects, we're not going to see the time differences. It's really where we get into these higher type number of items. So if we have 100, 200, 300, that's where we can actually see this stuff happen. The big takeaway here is anytime you see this n squared, this exponential growth, that is bad. That is something you don't want to see. Linear growth is pretty decent. There are a lot of other growths here. I just simplified this to have 3, just because I think that's the most important takeaway. And then if you can get this constant time, then you are doing awesome. This is really hard to achieve, by the way. Let's take a look at the next slide that shows just how drastic these things can be. So again, I have my constant time, I have my linear, and I have my exponential. So you see with one item, these are the items in the yellow box. You see there's not much difference. A human's not going to be able to tell, oh, this took 1 second versus this. It's going to be quick. It's going to be almost instantaneous. Now when we get outside of that yellow box, so if we remember, if we go outside of this yellow box now I'll see what happens. So this constant time still remains. Linear starts to pick up. You see between 1,000 and this large number here, 1,000,000, you have 0.1 seconds compared to 100 seconds. Now look at exponential growth. For 1,000 items, you're going to have 100 seconds. For a million, you're going to take 3 years for this to accomplish its goal. So now let's talk about these search algorithms. This should be a review because you should have had this in your C++ course. Linear search is also known as sequential search. You start at the first element and you step through. So you examine each element until it locates the value it's searching for. This one is pretty easy to understand. You're just going one by one. If you think about it, the worst case would be it's not in the list at all. So you process through all of the elements and you realize, oh, it wasn't in here. The other case that's bad is it's the last element. So you process all the way through and it's the very last one. Middle ground would be it's right in the middle. And the best case would be it's the very first one. So you're searching through this million element array and the first item you find is the item you're actually looking for. And that's best case. So what runtime do you think of this one is? I'll let you think about that. So here's an example of what I was talking about. So when we search for 11, we go through this whole thing and we never find it. When we search for 1, this is the best case. We find it right away. And when we search for 34, it's the very last one. So to me, it seems like it's dependent on the number of elements, which sounds a lot like a big O notation that I've mentioned. So here's the trade-offs. So the benefits of linear search, it's really easy to understand. The array doesn't have to be ordered. So if you remember from our previous slide, the elements are out of order. So some search algorithms that we're going to look at have to be ordered. So for instance, 1 would be first and then 4 would have to be second. So before you begin the search, you actually have to order the array first. Linear search, you don't have to worry about that. Now, what are the disadvantages? I've already talked about some of them. Let's say you have 1 million elements. So we're talking a super large array. Now, on average, it's going to be, 500,000? But worst case, and for things that aren't in the array, it's going to be 1 million. This probably isn't the best algorithm to use for large data sets. This is where binary search comes into play. So binary search, you see I underlined and put in red the order. This has to be ordered. So to use this search, the array has to be in order. And what it does, it basically goes through and it picks a middle point and then it divides it. It says, okay, there's going to be a left side and a right side. The stuff on the left side is going to be less than the stuff on the right side. And if you get lucky and you go to the middle and it's your value, you're done. So that would be, close to a constant runtime. So you'll notice one of the benefits right away. When you have everything on the left side is less than everything on the right side, if I'm searching for a number and I determine, you know what, it's less than this middle value, that means I go to the left side and I don't have to worry about this middle value or all of the stuff on the right side. So I repeat this over and over again. So you see how the values keep halving, and that provides a lot of speed benefits. If I search for 1 using a binary search, how would I do this? If you said, I can't do this because this isn't ordered, that is the correct answer. I wanted to reiterate that before you do a binary search, these have to be in order. So a linear search could work just fine on this one, right? It would search for 1 at the first spot and find it and return it. But for our binary search, we have to order it first. Here is the binary search in order. And now how does this work? So if I'm searching for 17, in my code, I'm going to take half of this array. And it just so happens that half of this is 17. So this is what I was looking for. So this is awesome. If I search for 1, I go up to the 17 and I realize 1 is definitely less than 17. So then I come over here. 1 is definitely less than 4. And there's my match. And the same thing for 34. You go up to 17, which is in the half. You realize, oh, it's larger than 17. So I come over here to the middle and I find my number 34. So what are the benefits? Well, it's more efficient than linear search, as we've seen, and it performs logarithmic n comparisons. This is a binary logarithm. So this is the power to which 2 must be raised to reach n. So if there were log 2 32, then the number of comparisons would be 5. Disadvantage, you have to sort it first. So that's going to increase your time. So that was just a quick intro to Big O notation and some of the searches that we use. For the sorts, I will let you look into the sorting algorithms. They're posted on Moodle, and there's Java code for those. There's also Java code for the search algorithms as well. Hopefully this cleared up any confusion, and if you have questions, please let me know.